which crosses right across the university, aiming to bring together lots of different disciplines to tackle a broad range of sustainability issues and working in partnership with external bodies as well. Part of the work we do as an institute is try and also disseminate some of the exciting innovations and developments in the field of sustainability to a wider audience, and that is of course one of the purposes of today's event. So thank you very much for joining us on what is actually at the moment quite a sunny evening, here at least. So just in terms of a few housekeeping elements, if you could keep yourself on mute throughout the talk. There will be lots of opportunities for questions at the end of the talk, but we'll let Chris run uninterrupted until the end. In terms of how to ask questions, so for those of you who have access to the chat function on Teams, then please add your questions into the chat, and then I will attempt to do a job of picking those out and firing them to Chris at the end. If you don't have access to the chat, and we realise it's a problem with this sort of Teams function, then you can email myself as the chair of the session with a question if you don't want to ask it out loud. And you hopefully will see my name there, which is Zoe Robinson. And actually the best thing is for you to probably just Google my name and Keele University, and you will find my contact details rather than me read out an email address, because I can't put it in the chat because you won't read it to be able to access it. Or alternatively, at the end, we will allow you to unmute yourself to ask questions yourself. So we'll have those two different ways of asking questions towards the end. As you might have noticed, a recording has started banner has come up, and that is because we are recording this session to further be able to disseminate the world of hydrogen to a wider audience beyond this talk itself. If you don't want to appear in the recording in any way, then I suggest you take your video off. And in fact, if you take your video off, it will also reduce the size of the recording, so that can be helpful. And also, obviously, we will carry on recording in the questions. So if you would rather your question was asked by someone else rather than you are on that recording, then contact me either through the chat or, as I've said, through email, and I'll read those out. OK, that's all for housekeeping. So on to the main business. It's a real delight to welcome Chris Manson-Whitton to give a talk to us this evening, and to be able to introduce Chris. So I've been lucky enough to have worked with Chris for probably, I don't know if it's 2 or 3 years now, linked to the HyDeploy project and the work that's been going on at Keele around the HyDeploy project. And I'd like to say I've learned a huge amount about hydrogen, but also actually how to get things done, and not just talk about changes, but actually make changes, and also work with diverse groups from residents through to policymakers to really try and drive that change. Just a note that there is a bit of feedback, so if people could make sure that they have themselves on mute. So there is definitely someone in the background, so you put yourself on mute, that would be great. So anyway, I've been very lucky to have learnt a lot from Chris over the last few years. I hope that you all learn a lot in the next hour. And so really just to introduce Chris Manson-Whitton, who's a director of Progressive Energy. He'll say more about that company, and really, Chris is an absolute leading figure in the world of hydrogen, so we're very lucky to have him giving up an hour of his time now. So over to you, Chris, and the hydrogen-powered revolution.
Fantastic. Thank you, Zoe, for that really kind introduction. Yeah, it's been a real pleasure to work with Zoe, with Chris, with Jeremy, and so many others at Keel over the last, well, I've been working with Keel over the last 4 years, so been really good. So let me just get a presentation up. So bear with me a moment as I do that. Let's just check. And Zoe, it would probably be useful if you could just confirm to me that that has all worked.
Yeah, we can see that.
Okay. Yeah, I'm just going to minimize that. I think that will work.
I should also just say, I've just heard that other people can't see a chat function, in which case we will just go for the people asking questions live at the end of the session. Sorry, Chris, over to you again.
No, thank you, Zoe. So yes, welcome to this lecture. I hope to be able to do 2 things, I think. On the one hand, as Zoe said earlier, actually, it would be good to give you an overview and context as to our energy system here in the UK, how we're going to decarbonise it, and the role that hydrogen has. But then the other side I'd like to cover is to use HyNet, which is a project that we have been delivering over the last 3 or 4 years, and will be continuing to do so as a case study to show how these kind of good theoretical ideas can be grounded in reality. And it's to give you that mixture of both, you know, what could we do and how can we actually do it? So join me for the journey. So this is a photo of my youngest child. She is now 11. She's not doing some form of extreme social distancing here. She was actually on a bungee, having jumped off a tall structure at a local play area near us. But Iris here is going to be younger than I am today in 2050. So we talk about 2050 and net zero by 2050 as if this is some other world that will happen down the line. But actually, it is really imminent and really soon. And the decisions we make today are going to affect the world of, well, in fact, it can affect our world as well as the world of our children. So those decisions she will make, are affected by the decisions that we make today. So, who are we? Progressive Energy. We're an organisation founded back in 1998, and our mission at that point, and still is to deliver material reductions in carbon emissions. That is our purpose. And the way in which we do it is by effective collaboration with other parties. So Progressive itself, we've actually grown. We are now over 25 people, moving on towards 30. In fact, when I started the project at Keel, we were less than 20. So we've got a lot of things have been going on recently. But the way in which we can make a difference is by partnering with large organizations who have the ability to see things delivered. But often those large organizations on their own can't see either how their piece in the jigsaw fits more widely or how they can collaborate with others. So when we talk about HyNet, you will see that it's a true consortium being delivered. So what does net zero 2050 mean? Well, if you start at the figure in the middle of this, I've taken this from the Committee on Climate Change's 6th carbon budget. You see that you look at the UK's emissions of, just under 900 million tonnes back in 1990. You see what's happened by 2018, and you can see it's almost a straight line in terms of coming down there and coming down to 2050. Yes, it's a slight increase, but fundamentally it looks as though we're on a reasonably straight line trajectory to 2050. So, okay, so what's the big problem? We just have to do more of what we've done before. But actually, the story is a little bit more subtle than that. So first of all, if you look on the left, this is a chart which was done by Neil Kay, who works with the Met Office. And I found this a really sobering chart. So this is looking at the total fossil carbon emissions ever emitted. I mean, realistically, most of those are since the middle of the 1700s, but the total fossil carbon emissions in the world to date, and what proportion of those have been emitted in my lifetime. So I'm 47, so I'm sitting down, let's call it the 45 age chart there, and 70% of those emissions have happened in my lifetime. Even my 15-year-old son, 30%, a third of the emissions have happened in his lifetime. So you can see that actually that rate of change that has happened is enormous, and we've got to turn that ship around. And the other thing is, if we take the figure on the right, and this is really quite important too. So if we look at what you could call our stack emissions, the emissions of carbon dioxide that we physically emit in this country, 1990, slightly different basis. They both come from CCC, but they're on slightly different basis. But the UK territorial emissions, again, around 800 million tons of CO2 per annum, came down quite significantly, and you can see that on that measure we were somewhere between 400 and 500 by the time we got to 2017. Nice downward red line. The challenge is that actually the emissions that we consume related to what we consume hasn't seen a trajectory like that. So the blue line tracks our total emissions, including our consumption as well, and you can see they rose quite noticeably up to around 2008. We'll see that's probably linked to the financial crashes, quite a key determinant there. Came back down again, but fundamentally in 2016 the numbers were not all that different from the mid-1990s. And so that says we do have a challenge in genuinely reducing our emissions and not simply offshoring them to other places. So we need to tackle both. But net zero, what does it mean? Net zero means there is nowhere to hide. When we had an 80% reduction, it was amazing how many organisations, sectors thought that they would get the remaining 20%. Actually now we need all the solutions in order to do it. And one of the themes in what I'm going to talk about today is it's not just about what the primary source of energy is, but it's about the vector that gets the energy from where it arises to where we need it. So I'm going to pick through some of the key energy demands that we have in the UK and look at what their drivers are to change them and what potential solutions there are. So industry is a big emitter of CO2. Why does it need to tackle its carbon intensity requirements? Well, one is that there is now an increasing corporate and social responsibility that organisations are under in order to actually demonstrate that they're doing the right thing. That's driven quite significantly by customer demands. So customers actually want products, solutions that are low carbon, and investors want to invest in low carbon solutions. But the other side of it is actually really quite significant economic threat. Across the world, generally, particularly in the UK and in Europe, we are starting to price carbon. So if we emit carbon, you have to pay to do so. And that, when you look at the profitability of a lot of our organisations in the UK, so the profit margin they've got relative to the size of the carbon changes that they could get over the next 5 to 10 years, that really does place a significant economic threat. So industry needs to tackle. What are the solutions? Well, obviously they can be more energy efficient. Where they have burnt or they have created carbon dioxide, they could capture it, or where they're using energy, they could switch to different fuels. So typically from natural gas, could go to electricity or to biomass or to hydrogen. Let's pick another area, domestic heat. What are the challenges in decarbonising domestic heat? Now, the graph in the middle, I'm sorry, it's not terribly clear, but it's an old version of a graph that actually Robert Sanson did at Imperial College, must be over a decade ago now. There have been other versions of it since. But what you can see in red is actually the half-hour demand of gas over a year. And what you can see in grey is the half-hour demand of electricity across the year. And we all tend to think that electricity demand varies quite significantly during the day and to some degree over the year, but mainly during the day. You know, when everyone comes home, they put the kettle on, they put the TV on, that kind of thing, then you get a bit of a spike. But look at it, the spike is nothing like the variation that you actually get on the gas network, both within a day, so in the middle of the night when no one's got their heating on, nobody's cooking, it's relatively low. Everybody gets up at a similar time in the day, massive firing up of boilers across the country, cookers going on, all sorts of things, and the same kind of thing at around tea time when people come home. And then you look at the variation that you get during the year. You know, on a July summer at 3 a.m, there's hardly any gas flowing around the network. But on December, when it's bitterly cold and there's a high over the country, you can find the demand is enormous. So that is how the energy is currently being delivered. And 23 million homes in the UK are on gas. That's around 83% of them. And I'm going to use a unit of terawatt hours. So when you get your gas bill or your electricity bill at home, you have a unit. And a unit is a kilowatt hour. And so obviously a terawatt hour, you go from kilo to giga, and then you end, kilo to mega to giga to terawatt hour. So we've got, 9 orders of magnitude bigger to get up to terawatt hours. So a normal home will probably use between 10 and 20 terawatt hours of gas. Nowadays, we're looking to more like 10. And then you can see here that we are dealing with 9 orders of magnitude bigger across the whole UK. So what are the challenges in decarbonising heat? Our housing stock is very old and quite mixed, and it's worth noting that by 2050, 80% of the homes that will exist in 2050 already exist. So there's lots of things we can do with the 20% yet to be built, but there is a huge amount to do that we've got to tackle with the 80% that we've already got. So what are the solutions? Clearly energy efficiency, insulation, and I've done a huge amount of insulation here in my house, and I know a lot of other people have. I know we've had a few debacles with how that works here in the UK, but we do need to do that. And then the other thing we can do is to switch to different fuels. And again, from natural gas, really our options are electricity, biomass, or potentially hydrogen. Electricity, we use heat pumps, and that is a good way of efficiently getting electricity. Can then be used very efficiently to generate heat by harvesting heat either from the air or from the ground, but it is a very different type of heat than you get from a gas boiler, and therefore the ability to rapidly heat up houses, and particularly houses that are leaky in terms of their energy efficiency, there are some challenges. So the opportunities with electricity solutions suit some properties, need some remedial work, but actually some properties are a bit more of a challenge. And high heat from either gas, from hydrogen, or even biomass can be a solution. Dispatchable power. So here in the UK, so dispatchable power means power when we need it. So we have had brilliant progress here in the UK in terms of our renewable electricity. We're absolutely massive increase, and I'll show you some of the graphs in a little while. The challenge, of course, is that the sun doesn't always blow, the sun doesn't always shine, the wind doesn't always blow. How do we balance the system? What happens on that when we've got a high over the country in winter and none of the wind turbines are moving, and yet it's very cold and we need energy? Furthermore, how do we handle the increases? So we know electric vehicles are becoming increasingly how we get around, and we'll talk about that in a moment as well. And that's absolutely right, but that will add a burden to our electricity system, and heat pumps will also add another duty to that. So how do we handle dispatchable power? Well, one is to do things with looking at our demand patterns and trying to shift them. One is to store electricity. That's certainly possible, but actually batteries at the kind of grid scale haven't been fully developed yet and are very costly. We could have generation that we can bring on, power generation we can bring online very rapidly. And if we do that, of course, currently we do that with natural gas. How can we do that in the future? And I think 2 very key ways are either to use hydrogen, so you use the hydrogen for that power generation, or you generate from gas and you have CO2 capture. So some of those key areas we've now covered: industrial, domestic heat, dispatchable power, and then the final one we're looking at is mobility. And electric vehicles are clearly gaining traction rapidly. We've had strong policy signals for that. I don't think in 20 years we will believe what we did today. So the fact that in Oxford Street you might have effectively 1,000 small incinerators, combustors burning away, burning fossil fuel in the middle of a pedestrian filled area in a city, which is what we are still doing today, will be as much an anathema in 20 or 30 years as it is that we used to burn coal and other smoke filled fuel for fires and things in cities in years gone by. I think that will move forward, and we will definitely see electrification. It makes so much sense and makes a lot of sense. But what about larger vehicles, buses, heavy goods vehicles, and even trains beyond electrification range? What are the challenges? They need a bigger range. They've got a charge time that they would need to handle. You know, a big HGV runs the risk of most of its payload becoming the battery that is there to power it. So what are the solutions? So one is to find biofuels that can just drop in for what liquid fuels happen today, and we all do that at the moment. There's up to 10% biofuels that we find in our fuel mix today. But that only gets us so far. Substitute, so CNG, compressed natural gas, and we can use bio-natural gas, so from anaerobic digestion. And we're seeing increasing number of large trucks running on compressed bio-natural gas here in the UK, which is a good solution. But ultimately, the other one is potentially hydrogen too. So a range of solutions. Let's just have a little look at the UK's energy mix to understand the scale of the problem. So here I am again in terawatt hours, and I'm taking the 2019 energy consumption in the UK. Now, there are some subtleties in there, but this is the end energy consumption. So this isn't the raw energy that goes in, but it's the energy that is being consumed in the UK by our consumers. And you can see, unsurprisingly, this is dominated by petroleum-based products, followed fairly closely by natural gas. We've then got this category called other, and actually in there is grouped a number of things. There's coal and other products made from coal, and interestingly, that's a lot smaller than it used to be even 5-10 years ago. And also this does include biomass and waste in particular as well, and the use of waste for energy. And then we've got this chunk which is sort of maybe 17-18%, which is electricity. And we've done really well on that electricity. Now for 2019, just over 50% of that electricity was low carbon, taken averaged over the whole year. So that means that electricity, and if you looked at it as a split on this particular graph, we're talking maybe 8 or 9% on this basis is low carbon of the total energy that's being used. Yes, there's some in that orange spot as well, but you can see the vast majority, basically 90% of that energy that we use in the UK is fossil based. And even though we've done brilliantly on electricity, there is a huge distance to go. But there are some challenges as well. So if we look down at this graph, which is looking at March 2021, now I haven't got the full key on here, I apologize, but at least it gives you a picture. The two that I am most interested in is here in blue, we have the wind generation contribution over the course of March. And you can see at absolute peak, wind generation was providing 54% of the electricity on our network. But actually at its minima, when we had, again, a very still period and it was deeply cold in March, it was only 2.3% of wind generation. Meanwhile, on the gas, which is this pinky one up here, 56% of it was at its max, but even at its minimum, it was still 12%. So looking at an annual figure is interesting, but you can see we've still got 90% of what's going on in our energy system is fossil derived. Looking on a month or a daily basis, the mix is constantly changing and we're needing to balance to deliver what it is that we need. And this is the challenge. What have fossil fuels done for us? The trouble is they're absolutely brilliant. They're in plentiful supply. They're very energy dense and easy to transport. They're easy to store. They're pretty much always there when we need them. They are fundamentally cheap compared with other sources of energy. They're concentrated sunlight from millennia ago that have been turned into a product that is in one location, easy to get out, and provides a huge dense source of energy. And we've built the fabric of our society out of them. So it's going to be a journey to wean ourselves off. This isn't something that you can just turn off and turn on again. If we doubled the amount of low carbon electricity we put on the system, we'd only make it from 10% of our system to around 20% of our system. So that's a huge change in electricity, but we'd still have 80% that we've got to try and tackle. The thing is, we have to find ourselves a way of weaning off, but it is going to be a journey. And that journey has behavioural implications. We have really got used to cheap and ready energy. It was really interesting. I just took this photograph off the web. You know, you could just go and buy a rheostat off there. Really interesting that the number on that is 22 degrees. I think if we talk to people from 20 or 30 years ago, the thought of keeping your home at 22 degrees would probably be alien to them. You know, it is a good number of degrees higher than we used to have. I mean, you look at this photo, it's not a great one, but I was trying to find, I'd seen a really good one somewhere, but I just wanted to show this one. This is a house clearly in winter because there are no leaves on the trees, and yet you see there are windows that are open. And I think generations before us, or even in earlier times, we tended to put jumpers on, we tended to keep the windows open, lots of air going on. We didn't keep ourselves quite so warm. And similarly, you know, transportation. We used to walk, we used to jump on bikes. So there are going to be big behavioural implications that we're going to have to deal with as we move forward. And what we need is a suite of solutions. We need all the tools in the book to get us to net zero. So although I am now going to spend quite a bit of time talking about hydrogen and carbon capture and storage, we absolutely need energy efficiency. There is absolutely a role for our biomass resources in what we're doing, and there is a real role for electricity, but we need this suite of all of them to work together. So let's talk about hydrogen. So low carbon hydrogen has been now recognised as one of the key tools in that toolbook. And whoever you look at, whether you look at the Committee on Climate Change, whether you look at national grid scenarios, or any number of consultants, or indeed, you know, recent government white paper, they are all clear that significant volumes of low carbon hydrogen is required. And in terms of significant volumes, they range from just under 200 to some of them even suggest up to 500 terawatt hours of hydrogen. So let me remind you, our domestic properties use around 300 terawatt hours across the UK. So we need as much hydrogen as they are being delivered today to our domestic homes on the gas network system. And why is that? Because hydrogen gives you solutions for some of those areas I've talked about: energy intensive industries, role in domestic and commercial heating, role in transport for larger vehicles, and a role in flexible generation to balance the grid, to enable more low carbon renewables by helping to balance them out. Where do we get hydrogen from? Now, hydrogen, yes, is an abundant element, but it is not necessarily there in ways that we can use and that give us energy. So yes, water contains H2O, but we need to extract it. And actually, in that regard, hydrogen is can be a source of energy, but is also importantly a vector by which energy is transferred. So there are a number of types of hydrogen. I'm going to talk briefly about them. So one, which is commonly called blue hydrogen, is taking the hydrogen out of something like methane and then storing the CO2. So we take methane from a gas field that's been stored for millennia. We take that out, we take the hydrogen, and then we take the CO2, we put the CO2 back where that methane came from, back into those offshore reservoirs, and then we have the hydrogen that we can use. And that's done by a number of processes, reforming processes that allow us to do that. And that can be done very efficiently. Up to 97% capture rate can be achieved of the CO2. So that's one approach. Another approach is electrolysis, so taking that hydrogen in water, using electricity to split it, and then taking the hydrogen. And that obviously can use electricity. Clearly, if it's using renewable electricity, then it is a low carbon solution. And potentially, we may be able to take the hydrogen out of biomass. So we take biomass, which is made of, like all organic matter, of carbon, hydrogen, oxygen, and a few other things, and using processes either biological or thermal processes to convert that into what's called a synthesis gas, and then upgrading that to hydrogen and CO2. Take the CO2, and then you can take the hydrogen, and then you can either just release the CO2, or better still, store the CO2, and at which point, as we'll learn a little bit later, that is considered a greenhouse gas reduction technique. And the key thing in determining which of these sources we use are issues like scale, cost, maturity. Do we have the resources? What are the carbon intensities? And that's one of the things that we'll cover as we go through this presentation. I talked about that build up to get that 300 terawatt hours of hydrogen. Here I've just shown how that could build up over time and in the different sectors. So you can see, we see industrials over time become quite a significant and important part, particularly in the 2030s, of consumers of hydrogen, and I'll show you some of the work we're doing on there. Similarly for CHP and power applications. You can see there's this grey area which is blending. So this is what we've done at Kiel, and Kiel, the project at Kiel is really unlocked. That plays a role particularly during the 20s, rising to the 30s. But then here we could envisage that parts of our gas network today using methane could convert and operate on hydrogen, and that is the yellow area that I've shown there. Then the light blue, a role for transport increasing, and then we do use hydrogen today in chemical solutions, and clearly using low carbon hydrogen is really important. So that's just a view as to how the role of hydrogen might build up by the end uses. I'm now going to talk to you about HyNet. This is the project that we've been leading, and I'd like to consider this as a case study as to how hydrogen can be involved across our energy system. Now, this is what's called an industrial, low carbon industrial cluster, which is based, as you can see, in the Liverpool-Manchester part of the country up in the northwest. But it's also worth saying that there are other clusters around the country, in Humberside, Teesside, up in Scotland, also in South Wales, looking to do similar things, although I think the HyNet one is by far the most advanced and has hydrogen most embedded into how it is structured. So what we have here in this cartoon, and it is a cartoon, but it shows schematically what's going on, is at the heart of it, we have a hydrogen production facility, which is taking natural gas and converting that natural gas into hydrogen and CO2. The CO2 is going down this orange pipeline, which currently is a natural gas pipeline from a gas store, a gas field in the Liverpool Bay, which is currently producing natural gas and bringing it onshore, but is reaching the end of its economic life now and is absolutely suited to be repurposed as a store of CO2 for flowing back down in this direction. There is a short amount of new pipeline to be built, but most of that exists in the pipeline, and the offshore assets already exist. So that then gives us hydrogen production, which we can grow at volume. That's the primary source of hydrogen for the foreseeable future, but over time we would expect by the time we get to 2050 there'll be many more other sources of hydrogen locking in there, that green hydrogen from electrolysis and potentially biohydrogen too. So we'll see a mix of different forms of hydrogen going into the infrastructure. And in black, what we have is a dedicated hydrogen distribution infrastructure, which is taking that hydrogen to a range of users. It's taking it to industrial users, so large industrial users both close to the plant and further afield. It's taking it to power generation sites, where they are going to be generating dispatchable power to match to that intermittent generation that's coming from offshore wind, which itself could actually also link into hydrogen when there is wind that could not otherwise, electricity otherwise couldn't be used. To do that, of course, hydrogen storage is important. And here in the northwest, we actually have some salt fields that are currently used for natural gas storage, which will then be developed for hydrogen storage and give us significant volumes of hydrogen store available. And then importantly, this black network then interlinks with the current natural gas network, which then allows us to blend a proportion of hydrogen into that natural gas network to start building on the good work that we've done at Kiel. So starting to decarbonise people's homes, with eventually the prospect that actually big chunks of that gas network could be fully converted to hydrogen. And we'll talk about that a bit later. And then, of course, we've talked about fueling and of transport, whether it's trains or HGVs. So this is the map of this HyNet vision that we have put together and we are now delivering. So it is the UK's leading hydrogen and CCUS project. The government has its 10-point plan. It has set certain targets in terms of how much hydrogen production it wants by 2030 and how much CO2 it wants to store using the kind of geological formations we've talked about. And HyNet can deliver around 80% of that hydrogen production target and potentially up to 100% of that CO2 storage target. It also has the prospect of potentially bringing home to the UK's first hydrogen village or hydrogen town actually being dedicated on 100% hydrogen, which is another part of that 10-point plan. Now, I said earlier, Progressive is a relatively small company. We achieve what we do by working with other people. And these are some of the big organisations based up in the Northwest that we are actually partnered with in terms of delivery of the plan. And I'll show you what role they have as we go forward. So we talked about the carbon capture and storage infrastructure. This we are developing with Eni. So Eni is the Italian state oil and gas company. Huge amount of work they've done looking at the offshore reservoirs that have been gas tight for millennia and we've used to produce natural gas as to their suitability for putting CO2 and storing it again. And people talk about CO2 storage as being something that is new. It has actually been done across the world for decades and is done in the North Sea today. So this is not something that is new, but actually commercially rolling it out at scale is. So they've done a lot of work on that and a lot of technical work we've done with them on the transport of CO2 by pipeline from where it arises to where it needs to be. An important part of that is not just taking CO2 from hydrogen production, but actually from some of our big industrials that produce CO2, not because of the fuel that they use, but because of the chemistry of what they're doing. And so we've got a fertilizer plant that will be putting nearly 500,000 tons of CO2 into the system. We're working with Hanson Cement Industry, who have CO2 production from their facilities that will link into the CO2 pipeline. And there is a big refinery up in the Northwest where some of their CO2, again, is chemical as part of their cracker. And we're working with them to capture around 800,000 tons of CO2 from that process to go into the infrastructure. But as I said earlier, at the heart of what we've got in HyNet is large-scale hydrogen production. And we're working with Johnson Matthey, UK company with world-leading technology for converting natural gas into low-carbon hydrogen, separating out the CO2. As I said earlier, with a 97% capture rate, so very high capture rate of CO2, which is then put into the infrastructure. We're working with a large engineering contractor, SNC-Lavalin, and we're currently doing what's called front-end engineering design. So it's a feed program that enables us to define the design of that plant. And we are in partnership with Essar, who own the refinery up there, and looking to build not only this first line, which we're working on at the moment, which will produce 3 terawatt hours of hydrogen. So come back to that 300 that we were aiming for. This is the first 1%. But interestingly, this is of the order of magnitude of the amount of biomethane that is produced in the UK. And this is just from one plant. But actually, then we'll be looking to build a second line at double the scale pretty soon after, and then 2 larger ones that will come after that. So that's the hydrogen production. And then we have this hydrogen distribution and storage infrastructure, which we're working with Cadent. So Cadent work in the Kiel region, and they also work in the Northwest, and they will be building an 80-kilometre hydrogen pipeline system that connects the production to all those users that we talked about, and also to the storage. And then we're working with the partners, part of the INEOS company with Innovin, who own the fields that are being used for the hydrogen storage. We will be storing 1 terawatt hour of hydrogen. So that is equivalent to 1/3 of a year of production from that first line. And again, just to put it in context, that terawatt hour of hydrogen storage is 1,000 times bigger than the world's largest battery. So huge opportunity for storing energy simply and at low cost. And then we're working with lots of the industry up there as well. So what we've got up here is around the 30 organisations that we are working with in the Northwest. Some of them are looking to capture CO2 directly. Those are the ones in orange on this chart. But you can see the vast majority are green dots, which show there are processes which could be switched from natural gas to run on hydrogen. And we've done a big piece of work with a UK burner manufacturer to demonstrate that a big boiler, a big burner, could operate on 100% hydrogen. And that's because we're doing some trials with Unilever at Port Sunlight. So Unilever make a lot of the bathroom and kitchen products that we have around the UK. They want to take one of their really big boilers, which is, significantly larger than, sort of 300 times larger than a domestic boiler, and operate that on hydrogen, as well as a blend. And we're also working with Pilkington. So Pilkington's glass manufacturer. Now they make sheet glass up in St Helens, and we will be working with them on one of their huge boilers, so that huge furnaces, which is yet another order of magnitude bigger. So we're now sort of thousands of times bigger than a domestic boiler, using hydrogen for making their float glass. That's going to be interesting, because not only do we have to be sure we can deliver all the thermal and technical and emissions requirements that we have there, the products of combustion come into contact with the glass itself. And what they'll be wanting to find out is to make sure that the glass maintains its quality even when we change the fuel. So we're working with these partners here. Now, blending into the gas grid. Now, this is something that's obviously close to Keel's heart. So this is taking hydrogen, mixing it with the natural gas that goes into the grid, and then delivering it to consumers. And the idea is to be blending at a level where neither the consumers nor the network have to make any changes. And it's a key enabling step in unlocking the hydrogen infrastructure. So it's a non-disruptive way of doing it, so nobody has to change anything in their homes, and it's a low-cost solution for early adoption. It actually saves a meaningful amount of carbon in its own right. It's equivalent to taking 2.5 million cars off the road. It helps us build up hydrogen production capacity, allows us to work with the regulators, the HSE, who are hugely important in this, to keep us all safe, and therefore understand the position with blending, and as a stepping stone towards potentially converting to 100%. We build up the supply chain. We help customers get used to the fact that hydrogen will become part of our energy mix, and of course unlocks the use of hydrogen more widely. So we've done this world-leading trial at Keel. It's been brilliant to partner with Keel on this. So you have effectively your own gas network, which is effectively typical of a small town. So we took an area of your network of around 100 domestic properties and about 30 of the university buildings. So quite big commercial applications there. And the purpose of that trial was to demonstrate that a blend of hydrogen and natural gas can be distributed and used safely in the UK network without disruption for consumers. So that was the objective of the project. We had to build the safety case. The UK has a brilliant safety and regulatory regime, and therefore we had to present evidence to the Health and Safety Executive that running at the 20% volume is as safe as natural gas. So we ended up doing around 18 months of extensive, rigorous research, including work that we did at Keel, including work we did with the health and safety laboratories in Buxton, in order to make that case. and then we secured permission for blending in November 2018. And again, this was some of the work we did going around testing existing properties and existing equipment and appliances at Keele University. Having done that, we built out the facilities, and those of you based at Keele will probably be familiar with the pictures on the left of the compound which we have there, and the good work that we did with people like Paul Richards and the estates team to actually construct that equipment. So that includes an electrolyzer to make hydrogen, which then gets put into a small intermediary store before it was then blended in this facility to go out onto the network. And then we had various tests, it being a proper testing research project. We were also testing composition out on the network and took various other measurements. And then we operated, and we were operating for over 15 months. It was slightly longer than we'd intended because of COVID, but we did that, and we finished in March this year. And in fact, we are now pulling together all of the results from that, and we're really looking forward to be able to share those with our friends at Keele, but also more widely as well, because this project is seen as being really key. One of the things we did do down in one of your big boiler houses was to take 8 boilers from 4 different manufacturers. One of each boiler was running on natural gas, one was on the blend, and those boilers were run really hard over the 15 months, effectively equivalent of pretty much a lifetime of boiler use. We've taken those off the wall. Those have now been sent to the various boiler manufacturers. Their mission is to first of all identify which boiler was running on natural gas and which one was on the blend, and if they could tell any difference. Now, those manufacturers stood behind the boilers in people's homes for the purposes of the trial. This is about establishing that for long life, over rolling this out, that they can stand behind those warranties as they sell those products. So we're collecting that data now. We had good operation, we had good network composition, and we've had no increase in leaks or faults on the network. So overall, been a really good project and some fantastic feedback. And there's one of the customers said, you know, I'm contributing by doing nothing. Where else do you get to do that? So it's saving carbon by not having to make major changes. So where does that lead us on to? Well, in fact, in Winlayton near Gateshead, we will be running a similar demonstration program on over 650 properties up in the northeast. So that will be over 1,200 domestic appliances. There's a really nice video from somebody that is involved in that, which if you just put Winlayton and NGN, so that's Northern Gas Networks, into YouTube search, you should find that. And there's a really nice little video of what we're doing up there. Currently, we're finalising the safety case with the Health and Safety Executive, building on all the really good work done at Keele. And we're looking forward to starting to operate there, subject to getting the safety case from the HSE in the next few months. And as I said, blending is a journey to 100% grid conversion. So boiler manufacturers here in the UK, Baxi and Worcester Bosch are the most well-known ones, have already developed hydrogen-ready boilers. So these are boilers you could go and buy today, run on natural gas, and if we end up with the transition over to 100% hydrogen, relatively straightforwardly with a gas engineer turning up, quarter an hour, half an hour, they can just turn that over and convert it to run on hydrogen. So there's lots of work being done in the UK, some big programs looking at the kind of safety cases we've put together for Keele, but for 100% hydrogen. And as part of that 10-point plan from Boris, we are looking to see a hydrogen neighbourhood by 23, a full hydrogen village by 25, and a town by 2030. This is a journey that we can be on and that can help decarbonise parts of our system. Now, as I said earlier, I would love to see heat pumps playing the role that they need to play. New build properties, I can see they have a really key role. Properties that we can insulate well and effectively, they have a key role too. But there's a tranche of properties for which I think hydrogen offers a solution of direct, rapidly heating up, allows us to get the heat into properties at the time that we need it. We need a patchwork. We need a mixture of all of these solutions. One final thing before I close is called greenhouse gas removal technologies, GGR. So when you look at the Committee on Climate Change has reviewed what we need to do to meet our net zero targets, we will achieve a lot by saving carbon from actually going out into the atmosphere. But at the end of the day, we're also going to need some ways of effectively removing carbon dioxide from our biosphere. And how can we do that? So one way is what's called direct air capture. And on the right-hand side, there's some schematics of ones that were produced by the IMECI a number of years ago. They're supposed to take CO2 from the air, capture it, and then take it away and sequester it. Now, the challenge with that is that air is just around 400 parts per million CO2. Now, that's a major problem, and it's the fact that it's going so high that it's causing a problem. But from a chemistry perspective, capturing that CO2 at atmospheric pressure is really quite difficult. But fundamentally, trees have been doing it for millennia. You know, biomass is a highly refined, self-replicating mechanism for capturing through photosynthesis carbon from the air. So what we can do is we can grow. Here I've shown willow, but I mean it can actually be other sources of biomass and potentially sources of biomass that have a first use, say in construction or in that kind of way. But then at the end of their life, you could then use, and you could then take that biomass and you could get both useful energy from it and potentially storing carbon. So what I've got here is an example of a project we're working on, which will also be up in the Northwest, is a project called Project Bright. And this is going to take refuse-derived fuel and potentially unrecyclable wood, and it will then convert that. The main thing that it will be converting into is to natural gas, a substitute natural gas. And that will reject a certain amount of CO2. That CO2 will then go into our sequestration system and will therefore be effectively taking CO2 out of the atmosphere, which has been captured by the biomass and the plants. We will then take from that some energy that we need, but also take the CO2 and store it. Now, if we're making methane, then we will still end up with just a bit more than half of the CO2 comes out at the point of use when you burn the methane. Clearly, if we make hydrogen, which is the alternative vector we could make, you could capture all of that CO2 and store it. And effectively, you are taking carbon out of the biosphere rather than from fossil fuel resources. So that's the plan up there, which is another part of looking to achieve our net zero goal. Now that's based on technology, which is currently finalising construction down in Swindon as a reference facility, which we're very excited about with one of the partners that we're working with. So how does that all fit together? So over this HyNet timeframe, we started working on HyNet back in 2016. We're currently in 2021, so you can see there's been a pretty big journey that we've been on to get to where we are now. We have just completing the engineering feed on the hydrogen production plant, and we're just starting that feed and consenting process for the CO2 infrastructure. So we'll be looking to make investment decisions on both of those back end of next year, early 2023, to allow us to be operating our first hydrogen production line and our CO2 infrastructure by 2025. And we've had really good support from BEIS, so government department, and now we're working with them on the policy regime to actually see this all built. So what does that do? We've talked about the carbon implications of what we're doing. It also underpins economic growth. So it underpins jobs, safeguards jobs that are there, brings inward investment into the region. The UK has got some fantastic skills based on its offshore oil and gas experience, as well as its chemical industries leadership. Those skills we can hone, and then we can be not only doing it here in the UK, but translating it further afield. And fundamentally, it gives us a sustainable path to net zero using CCS and hydrogen as part of that transition from relying on fossil fuel and letting the carbon go to the atmosphere, to using fossil fuels where we then deal with the carbon, to then translate ultimately to moving into green and other forms of hydrogen, which will slowly take their place in our energy mix to then give us our solutions that we need over time. So, can we solve it? Yeah, I believe we can. Good. Zoe, sorry, that went on probably just a few minutes longer than I intended to, but hopefully that's given everybody what they need.
Super. Thank you very much, Chris. And I'm sure you can hear the rapturous round of applause getting to. No, fantastic. And you know, I think such a positive talk and a positive view in terms of the trajectory we're on, and actually saying, you know, there are solutions that are being actively worked on. So Chris is happy to stay around for another 10 minutes or so to address sort of questions. Appreciate we're close on 6 o'clock, but I also, I'm sure, have some burning questions out there. I've had one question which has been emailed to me because of the lack of Teams chat, but I will ask him to ask it himself actually. So Richard Waller, would you like to ask your question? And if other people have questions, then please put your hand up. You can do that, and we'll ask those. Go for it, Rich.
First of all, just to say thank you very much for a fabulous talk. Really fascinating, and I agree entirely. A really important part of the journey towards a low carbon future. It's just one thing I've heard mentioned in the past as one of the sort of areas of concern, and just the energy costs associated with carbon capture and underground storage. So I was just wondering whether you could give us a little bit of an insight into just the energy demands of capturing that carbon, compressing it, transporting it, and injecting it into an underground reservoir.
Yeah, really good question and really important. So when people tend to think about CO2 capture and storage, they tend to think about taking a power station that's got a flue gas that is at atmospheric pressure and pretty low concentration of CO2. I mean, it's more than in the general atmosphere, but it's still only, you know, a few percent, depending on what the fuel is that's being burned. And you have to capture it. And you're right, doing that does entail a reasonable amount of energy in order to capture the CO2, because you tend to use a solvent that picks it up, and then typically you have to heat the solvent afterwards to release the CO2, and that takes energy. Now, some of that energy you can scavenge off, say, your power plant, and you get some of it that would otherwise be wasted. But often, you're right, you do need a reasonable amount of energy. And then you've got to compress the CO2. Now, the difference if you're making hydrogen is in our process, we have the hydrogen and CO2 at high pressure, so at around 40 bar, and high concentration. And on our plant, the energy we need to capture the CO2 is fully scavenged from the process itself. So actually, we end up with loads that are just fully serviced by what we're doing, which then gives you a pretty efficient process, which is why we believe that making a product like hydrogen, centralizing the capture of the CO2 using integrated, highly thermally integrated processes is a much better way of doing it than capturing CO2 from lots of parts of the chain.
Great, thank you very much.
That's right.
Thank you. Are there any other questions out there? I can't see any hands up. Chris, Fogwill.
Thanks, Chris. As usual, an absolutely wonderful talk. Thank you so much depth and interesting sort of angles on it there. It's amazing to see the timescales you're talking about. Obviously, it's really interesting from HyNet Northwest to actually see the infrastructural costs there. The funding behind this, obviously, I know there is significant funding in terms of BEIS and other support, but is it largely private? And does it provide the model that we need to show how quickly we can make that transition for hydrogen in this case? Because it's, like I say, the multifaceted uses of hydrogen. Does it provide the model, and is it something which, you know, people are really interested in exploring? Because, you know, getting that investment is going to be the key question for everyone, I guess.
Really good question. So I guess, can I split it into two things? One is the investment for the development, and one is the investment once you're actually building and operating the plant. So in the early stages, BEIS did very well in providing high levels of support. So they have actually funded the engineering on the hydrogen plant and those trials at Pilkington and Unilever in the same way as Ofgem funded the trials at Kiel, which is great. Government's moved a notch along. So for the work that we're now doing, HyNet is just starting a £70 million development programme, of which just under 40 million was from the private sector and just over 30 million was from government. So you can see at that point the balance is starting to change, with quite a bit of private sector going in alongside government, which is good. That's on the development side. What we're now working with government on is the support regime to enable commercial plants to actually be built. So if you'll remember, when offshore wind was first mooted and the early projects were receiving a fairly substantial subsidy. So electricity is nominally worth around £50 a megawatt hour. Those early offshore wind projects were receiving £150 a megawatt hour. So £100 of per megawatt hour of subsidy. And then that subsidy was funded by all the consumers across the UK contributing to that. So we all still buy our power fundamentally at that wholesale price, plus then we each chip in a tiny little amount, which together allows those low carbon facilities, offshore wind turbines, to be built. We've now seen the offshore wind turbines are now being built for less than £50 a megawatt hour. So that kind of investment in early plants we have all made by contributing has then brought the costs down to the point at which it's comparable with using natural gas, or in fact, potentially even cheaper. So we see a similar model for hydrogen, that there will be a support regime that allows early projects to get away. The costs are socialised across all of us. So, literally, a few pence that we all contribute that start to allow those early projects to take place. And then over time, the costs come down. But also over time, we are all going to have to start paying for the carbon that we emit. And as we start to factor in the cost of using fossil resources, then solutions that don't emit fossil resources will start to become cost competitive too. So it's things going in both directions. The important thing for policy is to make sure the way those costs are allocated is fair and just. And there are big questions about whether that's through taxation or whether it's on consumers and things. And government is wrestling with that now, as they have done in the past.
Yeah, no, that's a really good point, Chris. Thank you very, very much.
Thank you. Any other questions out there? Just scrolling down, checking I can't see any hands. In which case, I'm going to take Chair's prerogative and ask you one relating to again, the domestic heating question, which is, what do you see as the key barriers actually to that 100% hydrogen heating? And it's a bit of a two-part question, because if it becomes quite feasible, does that become an easier solution than actually retrofit, which might be a better solution?
Yeah, interesting question. So I think quite rightly, the first thing to do is all the good scientific work that's going on to make sure it is just as safe. So that's kind of a key starting point. I think there is an assumption that using hydrogen or not in the UK depends on the decision to convert the gas grid. And I would actually put that the other way round, that actually what we need is to see where hydrogen unequivocally has a role to play in industrials and things like that, which allows us to build up production. Because I think a key barrier is, if you want to convert a part of the network to run on hydrogen, you've got to deliver hydrogen as reliably as natural gas is delivered today. And we rely on that. You can't leave people in the cold in the middle of winter because they don't have heating there. So we need to build up the production side. And then I think there is a kind of policy is this the policy that we need to make? Those, I think, are the key things. In terms of the barriers to retrofit, I think they are quite significant. So first of all, I alluded to it, but insulating property. So I've ended up, the house that I'm living in now, I bought 18 months ago. I'm afraid it is heated by oil. And I seriously, because I'm not on the gas network, I seriously looked at trying to put a heat pump in. But this house, built in the 1920s, had virtually no insulation. So in the end, what I did was we've insulated. I mean, the room I'm in at the moment has got probably, it's not huge, but it's probably 120 millimeters of insulation on all of the ceilings and the sloped ceilings that I've got. And we've done external insulation as well. So I'm afraid we actually spent all our money on insulating rather than on the heat system. But hopefully, once I can see how this runs, then I will consider a heat pump potentially later, because I don't have another option. But I have the luxury of space, so I have actually got space to put in a storage tank if I need to. And again, that would be a different story if I was in a terrace property, I couldn't externally insulate it, I was solid brick wall, and I haven't got, I've ripped out my hot water tank in order to put a combi boiler in. I don't then have the space to put the equipment back in. And I think some of those practical issues are going to be the challenge. Which one is better? To be honest, I would take a view, you're going to end up using hydrogen to heat your home in either way. You're either going to use it directly into the home, directly delivered by hydrogen, or for the times when the wind isn't blowing and the sun isn't shining, the electricity used will probably have come from hydrogen in order to fill the gaps. So at which point, I'm never so keen on which is better or which is perfect. I think we're going to need a mixture of solutions, and over time we'll see which ones deliver most effectively and customers are most comfortable with.
Super, thanks, Chris. We've got two questions. Let's see if we can get through those in the remaining 7 minutes. I think will give us. Let's go so Sarah Briggs has put a question in which very much sort of relates, I think, to what we were just talking about. So what do you think is the best approach for homeowners whose central heating systems are coming up to needing replacement?
That is a really hard one, because fundamentally you can't use hydrogen immediately. Hydrogen is a journey that, depending on where you are in the country, could be 5 years, could be 10 years. We know that that the Worcester Bosch Baxi have produced hydrogen-ready boilers. I would like to think that, given that they are virtually the same cost as ordinary boilers, that actually, sorry, it's tea time in my household. I would like to think that government could consider mandating that all boilers are at least hydrogen ready, in the same way as all TVs before HD came along were HD ready. I think there's a role for that, because it's a no regrets kind of policy. In terms of what decisions should you make on the ground, I mean, your options on the ground are insulate your house completely, and I would say do that before you do anything else. It's not very sexy, it doesn't feel like it's the exciting thing to do, but it's the thing. If you can heat it with a candle, it doesn't really matter what the candle's made out of. That's to do that. And then other than that, I think heat pump, if you can do a heat pump, great. But bear in mind, it's a big capital outlay, and you need to be confident your property will work with it.
Super, thanks for that. I'm going to use that phrase about heating it with a candle. Good one. Yeah. And Jeremy, you had your hand up previously. Is that still a question that you want to ask?
Yeah, I'm sorry. I very recently read a very brief article on the ammonium alternative. Have you come across this?
So ammonia is considered as a way of transporting hydrogen from one place to another. So ammonia is what we use in the fertilizer industry. So there's a fairly big, trade in that across the world. Ammonia is fundamentally nitrogen and hydrogen, and so it is a stable and reasonably energy dense way of storing hydrogen, which you could crack at the point of use into hydrogen. So I think people are considering it. I think that will be a finessing of how we do hydrogen in the future, because I have a vision. I mean, let's face it, putting solar here in the UK is not necessarily a great thing to, I mean, it's worth doing, but really you want to do solar somewhere, equatorial. I have a vision that we'll end up with solar farms, across equatorial regions that will produce either electricity, if that can be taken away, or produce hydrogen, which could then be shipped around the world in the way that LNG is shipped around, natural gas is shipped around the world today. And in that world, ammonia could be another legitimate way of shipping the hydrogen vector around the world for it to be able to be used.
Super. Thank you so much for that, Chris, for a fantastic talk, and for some great, really full and detailed answers. So we're all much more clued up. So it sounds like dinner is ready, and therefore it's time to let you get on with the rest of your evening. So really, just thanks from Institute for Sustainable Futures and all of the participants today. Thank you very much.
Thank you. It's been a pleasure. Cheers.
Cheers, folks.